An IP fabric is one of the most flexible and scalable data center solutions available. The IP fabric's reliance on Layer 3 makes it a good fit for data centers with multiple vendors, as it does not involve proprietary features or protocols. Some of the most complicated tasks in building an IP fabric are assigning all of the details such as IP addresses, BGP autonomous system or AS numbers, routing policy, loopback address assignments, and many other implementation details. The network should scale linearly as the size increases using the three-stage fabric method developed by Charles Claus. Here the devices are referred to as nodes such as spine nodes and leaf nodes. Keep in mind that all devices in an IP fabric are basically Layer 3 routers that rely on routing information to make forwarding decisions. In the 1950s, Charles Claus first wrote about his idea of a non-blocking, multi-stage telephone switching architecture that would enable calls to be completed. The switches in his topology are called crossbar switches. A Claus network is based on a three-stage architecture: an ingress stage, a middle stage, and an egress stage. The theory is that there are multiple paths for a call to be switched through the network, such that calls will always be connected and not blocked by another call. The term Claus fabric came about later as people noticed that the pattern of links looked like threads in a woven piece of cloth. You should notice that the goal of the design is to provide connectivity from an ingress crossbar switch to an egress crossbar switch. There is no need for connectivity between crossbar switches that belong to the same stage. Here is the diagram of a three-stage fabric design. In an IP fabric, the ingress and egress stage crossbar switches are called leaf nodes. The middle stage crossbar switches are called spine nodes. In a spine leaf architecture, the goal is to share traffic loads over multiple paths through the fabric. A three-stage fabric design ensures that the access-facing port of any leaf node is exactly 2 hops from any other access-facing port on another leaf node. It is called a three-stage fabric because the forwarding path from any connected host is leaf, spine, and leaf, or 3 stages, regardless of where the destination host is connected to the fabric. Many applications function best when packets are received in the order in which they are sent. In an IP fabric design, per-flow traffic sharing should be implemented so that packets in a unique flow follow the same fabric path. This helps prevent out-of-order packets arriving at the destination host due to potential congestion or latency between different paths through the fabric. To maximize the throughput of the fabric, each leaf node should have a connection to each spine node. This ensures that each server-facing interface is always 2 hops away from any other server-facing interfaces. This creates a highly resilient fabric with multiple paths to all other devices. An important fact to keep in mind is that a member switch has no idea of its location, limited to twice the capacity of a single. The choice of router or a Layer 3 switches facing interface is always to each spine node. This ensures that each server-facing interface is always 2 hops away from any other server-facing interfaces. This creates a highly resilient fabric with multiple paths to all other devices. An important fact to keep in mind is that a member switch has no idea of its location spine or leaf in an IP fabric. The spine or leaf function is a matter of a device's physical location in the fabric. The choice of router or a Layer 3 switches to be used as spine nodes should be partially based on the interface speeds and number of ports that it supports. Currently, there are 2 prominent design options in an IP fabric architecture. Option 1 is a basic 3-stage architecture. Each leaf connects to every spine. The number of spines is determined by the number of leaf nodes and the throughput capacity required for leaf-to-leaf connectivity. In the diagram, a spine leaf topology with 2 spine devices and 4 leaf nodes is shown. The throughput capacity from one leaf to any other leaf is limited to twice the capacity of a single uplink, since there is a single uplink to each spine node. In the event of a spine device failure, the forwarding capacity from leaf to leaf is cut in half, which could lead to traffic congestion. This can be increased by adding additional uplinks to the spine nodes using technologies such as link aggregation group or lag. However, this type of design places a large amount of traffic on a few paths through the fabric. To increase scale and to reduce the impact of a single spine device failure in the fabric domain, additional spine devices can be added. If two more spine nodes were added to option 1, the traffic from leaf 1 to leaf 4 would have 4 equal cost paths for traffic sharing. In the event of a spine device failure or maintenance, it requires a spine device to be removed from the fabric. The forwarding capacity of the fabric would only be reduced by 1/4 instead of 1/2. For scalability and modularity, a layer 3 fabric can be broken up into groups of spine and leaf nodes. Each group of spine and leaf nodes is configured in a 3-stage fabric design. Each group is then interconnected through another fabric layer. Sometimes the groups of 3-stage devices are called pods, and the top tier of the fabric is called a superspine. Traffic within a pod does not leave the pod. Only interpod traffic must transit the 5-stage fabric or superspine. It is called a 5-stage fabric because the forwarding path from one host to another follows a leaf spine, superspine, spine, leaf path, or 5 stages. From the perspective of the superspine devices in the diagram, each spine level node is viewed as a leaf node of the superspine.
The table displays some of the recommended Juniper Networks products that can act as spine nodes. You should consider port density and scaling limitations when choosing the product to place in the spine location. Some of the pertinent features for a spine node include overlay networking support, Layer 2 and Layer 3 virtual extensible LAN or VXLAN gateway support, and number of VLANs supported.
The table displays some of the recommended Juniper Networks products that can act as leaf nodes. Some considerations when choosing leaf nodes include what type of server or host connectivity is currently required, and what types of server or host connectivity may be used in the future, such as link types, link speeds, and so on. Other considerations may include whether or not Layer 3 VXLAN gateway capabilities can be deployed on the spine or on the leaf nodes, and the number and speed of uplink ports.